Okay, chemical reactions rates. Chemical reactions rates are very important in chemistry in the industrial process, and often a chemical engineer has to have quite a lot of knowledge about chemical kinetics. So they use to design medications, improve techniques, and to develop more efficient methodologies. So chemical kinetics is a field of chemistry that studies rates of reaction, or how fast a reaction occurs. It's useful because then we can manipulate the speed as needed. So the reaction rate is the speed that a chemical reaction proceeds at. It can be expressed as a rate at which a product is formed, or a rate at which a reactant is consumed. So often a data is it's either going to be recorded by a machine that records data points, and perhaps even graphed. So let's say we have a graph. So time or reaction progress goes on the bottom, and then maybe concentration. Doesn't have to be concentration, but it's one of the measurements that are used to measure rate. And let's say we plot a graph. We plot a graph with products and reactants. So initially you have a certain amount of reactants, and as they get used up, they start to decrease. So that's your reactants. At the same time, your products are increasing. So when we measure rate, we actually tend to measure it right here at time equals 0, because when you do that, you're measuring the rate of change of your reactants, and there's no product molecules to get in the way of your collisions between your molecules. So we tend to do it there. When you are graphing, though, you can take, you can solve for your reaction rate by taking an average, and that would be between 2 points. Or if you want instantaneous, you can make a tangent. So tangent is for instantaneous rate at that particular time. Instantaneous. And then between 2 points will give you the average. So rate is equal to the change in a quantity over a change in time. Now, really important, it is always a positive quantity. So we record it as a positive quantity, and we do that by having a negative sign in front of our change in reactant concentrations. And that negative times a negative, because your reactant quantity will decrease, that will make a positive. Now these square brackets, if you're not used to seeing square brackets are used to represent concentration. Our units are going to be moles per liter for concentration. When you factor in the time, our units for rate are going to be moles per liter per second, or perhaps mole per liter per minute. So when we have the amount of products formed, it will be a positive value, and that is because it is increasing. So your change, your final concentration minus your initial concentration, is going to be positive. So these are going to be what I just showed you. They're average rates because it occurs between a time interval, whereas an instantaneous rate is taken at an instant in time. You can use mole ratios to convert between different substances if you're given the rate of one substance in the chemical equation. Okay, here, let's do an example. Dinitrogen pentoxide decomposes. I'll add a little bit of heat there to show that it's decomposing. Decomposes into nitrogen dioxide and oxygen gas. Okay, so initially we have 2.2 times 10 to the negative 1 moles per liter of dinitrogen pentoxide. And at 4 seconds, we have 1.0 times 10 to the negative 1 mole per liter. So time was 4 seconds. So this was initial, and this was after 4 seconds. Square brackets of concentration. Okay, so let's write out our expression. We want, it's negative because it's the reactant changing, so it's decreasing. Changing concentration of N2O5 with time is going to be the second concentration minus the first concentration over the time lapse. And this is negative. This is the negative change. All right, so 1 times 10 to the negative 1 minus 2.2 times 10 to the negative 1 over 4 seconds is equal to negative 3 times 10 to the negative 2 mole per liter per second. So this is 3 times 10 to the negative 2 moles per liter per second. So dinitrogen pentoxide decreases at a rate of 0.03 moles per liter per second. So now what if I want to know how much the rate of nitrogen dioxide is forming? So what you do there is you just take your mole ratio and you multiply your rate of change by your mole ratio. Okay, so the rate of change of dinitrogen pentoxide was 0.03, or 3 times 10 to the negative 2 moles per liter per second. So this is for N2O5. Now, to convert to one of our products, like nitrogen dioxide, you're going to multiply that by the mole ratio. So 4 NO2s are produced for every 2 N2O5s. So we got these numbers from the balanced chemical equation, right? The 4 was the coefficient for the NO2, and the 2 was the coefficient for the N2O5. We want N2O5 to go on the bottom so that it cancels. So now the rate of change of the formation, so now we've got rate of change of concentration in NO2 with time is going to be 0.03 times 4 divided by 2. So this is going to be 0.060 moles per liter per second. So once you have the rate of change of one species in your chemical equation, you can find the rest by converting using mole ratios. So rates change during a chemical reaction. It's not constant. Greatest rate occurs at the beginning as only reactant molecules are colliding. Chemists need ways to measure the changes, so we can use various different physical properties in order to measure rate. If you are forming a gas in your reaction, you can measure the volume change or the pressure change. Perhaps you can measure the change in mass because one of your products is escaping because it's a gas. Temperature, you could use a thermometer. Color change, you can use a spectrophotometer, and the change is the amount of absorptions of light with time. If you're doing an acid-base reaction, you can measure the change in pH. And ions, if they are being consumed or formed, you can measure the change in conductivity. So these are different ways to measure rate and how to calculate rate.